Hey everyone, welcome to our latest video. Today, we're diving into something super cool, a paper titled Self-Rewarding Language Models. It's a joint effort by some brilliant minds, Weijie Yuan, Richard Yuan-J Pang, Kyung-Yoon Cho, Sainbayar Sukbatar, and Jing Xu, hailing from Meta and New York University. So, grab your coffee, and let's unravel the innovative world of language models together. Get ready for some groundbreaking insights, and let's get started. Diving into the core of our discussion, this slide unravels the key findings of the paper. The team introduces an innovative concept, self-rewarding language models, a blend of instruction followers and reward models, cleverly coined as LLM as a judge. Picture this, a model that not only follows instructions but also judges and rewards itself. It's like having a student who learns and self-evaluates, constantly evolving. They've employed iterative training, growth, a method where the model is its own teacher, generating new training data in each cycle. Fascinatingly, with every iteration, two things happen. The model's ability to follow instructions sharpens, and its skill in reward modeling gets better. It's like watching a learner become wiser with each step. What's even more intriguing is how later iterations feed the model higher quality preference data, suggesting that these models might just outdo the limitations of human-provided seed data. It's a glimpse into a future where machines refine their learning process, surpassing our traditional methods. So, what's this study really about? Let's peel back the layers. The researchers are tackling a key bottleneck in current approaches to language models. They max out at human performance levels. Think of it as a runner hitting their speed limit. And here's another twist. The separate, unchanging, or frozen reward models can't level up during training. It's like having a coach who can't update their playbook. Enter the heroes of our story, self-rewarding language models. These aren't just any models. They're double agents, playing the role of both instruction followers and reward models. Imagine a multitasking wizard. And how do they do it? With a concept named LLM as a judge. It's like having a fair and wise judge inside the model, doling out rewards and guiding the learning journey. The ultimate goal? To create models that continually improve, breaking the ceiling of human preferences. It's like aspiring for a world record-breaking sprinter who keeps getting faster. Here's a quick example to tie it all together. Traditionally, a reward model R would give rewards to train an instruction-following model F. But in this innovative approach, there's a joint model G that wears both hats. It's like combining the coach and the athlete into one super entity. This study isn't just about building smarter models. It's about redefining the limits of machine learning. Stepping into the world of related works, let's see how this study stands out. Picture a landscape where reinforcement learning from human feedback, or RLHF, is the norm. Here, the reward models, frozen in time, are trained from human preferences, but they hit a ceiling. They can only be as good as human performance. It's like having a speed limit on a highway, beyond which you can't drive. Now, enter direct preference optimization, or DPO. This approach sidesteps the need for separate reward models. Think of it as a shortcut in the learning journey. Previous work on iterative DPO took things up a notch, outperforming standard DPO. It's akin to finding a more efficient route on our metaphorical highway. But here's the catch. Even iterative DPO still relies on a fixed external reward model. It's like having an improved car but still abiding by the same speed limit. To paint a clearer picture, in RLHF, a fixed reward model, denoted as R fixed, trains an instruction following model, denoted as F. In DPO, F is trained directly from human preferences, skipping the separate reward model. But the game changer in this study? A single joint model, denoted as G, that handles both roles, merging the best of both worlds. It's like having a self-improving, self-driving car that knows no speed limits. Now, let's zoom in and frame the problem at the heart of this study. When we look at standard reinforcement learning from human feedback, RLHF, or direct preference optimization, DPO, there's a common hitch. They're bottlenecked by fixed external rewards. It's like being in a race with a predetermined finish line. This brings us to some pivotal questions. First, is it possible for a model to enhance its own grasp of what constitutes good rewards? It's akin to asking if a runner can define their own finish line. And second, Can we step away from the constraints of fixed external rewards? Imagine a race where the track adapts to the runner, not the other way around. These questions challenge the traditional boundaries and push us to rethink how we approach the development of language models. It's not just about making incremental improvements, it's about reimagining the rules of the game. Venturing into the heart of this innovation, the team presents a sparkling solution to the problem we just framed. The core of this ingenious idea lies in what's called a self-rewarding language model, empowered by the LLM as a judge concept. It's like having a self-sustaining ecosystem within the model. The strategy? To train the model jointly on two fronts, following instructions and judging. Imagine a gymnast who not only performs but also scores their own routine. This approach allows the model to simultaneously and synergistically improve at both tasks. It's a bit like a dancer who learns to choreograph their own steps while dancing, growing more adept at both with each move. This isn't just a step forward, it's a leap into a future where models aren't just learning, they're self-evolving. As we delve deeper, let's unwrap the layers of the proposed method. The team's strategy focuses on joint training in instruction following and judging, like teaching a chef to both cook and critique their dishes. At the core is an iterative training loop, a continuous cycle of self-improvement. Here's how it unfolds. A model, let's call it M sub T, steps up as a creator, spinning out prompts and generating candidate responses. But it doesn't stop there. It then slips into the role of a judge, using the LLM as a judge mechanism to evaluate its own responses. Picture a painter who not only paints, but also curates their gallery. From these self-evaluations, the model constructs preference pairs, like a craftsman selecting the best tools for their trade. These preferences then become the training ground for the next model in line, M sub T plus 1, trained via iterative direct preference optimization. It's a relay race of learning, where each model passes the baton to a more refined version of itself, pushing the boundaries of what's possible with each iteration. Let's immerse ourselves in the intricacies of the proposed method, which is brilliantly illustrated in a figure captioned Self-Alignment Method Overview. Imagine a two-part symphony. In the first movement, titled Self-Instruction Creation, the model steps into the spotlight. It's a creative maestro, generating a symphony of prompts and responses. But it's not just a creator, it also dons the hat of a critic, scoring its own responses in a display of introspective critique. Then, as we transition to the second movement, instruction following training, the plot thickens. Here, the model, like a meticulous artisan, constructs preference pairs from the cacophony of its creations. This isn't just training, it's a sophisticated dance of iterative direct preference optimization. Each step in this process is like a brushstroke on a canvas, gradually painting a masterpiece of machine learning, where the model is both the artist and the muse. Now, let's waltz into the realm of key outcomes, a testament to the success of this innovative approach. Imagine a series of escalating triumphs with each iteration of the model. In the realm of instruction following, the win percentage climbs higher and higher, like a mountaineer conquering new peaks. By the time we reach iteration 3, it's a scene of celebration. This iteration outshines well-known players like Claude 2, Gemini Pro, and GPT-4 0613 on the Alpaca Eval leaderboard. It's not just a win, it's a leap over giants. And there's more. As the iterations advance, the responses become longer and of higher quality, like a writer whose novels grow richer with each publication. On the flip side, in the domain of reward modeling, we witness a similar rise in metrics. Think pairwise accuracy percentage, exact match percentage, and others, soaring like a rocket. It's as if the model is developing a finer palette for what makes a good response. It's breaking free from the shackles of fixed external rewards, charting its own course in the vast sea of possibilities. This is not just an improvement, it's a paradigm shift in how we understand and harness the potential of language models. Let's dive into a captivating visual, a prompt example for the LLM as a judge concept, which is central to the self-rewarding mechanism. Envision a snapshot that encapsulates the essence of the model's self-evaluation process. The figure elegantly illustrates the actual prompt used by the model to judge its own creations. This isn't just a routine check, it's a sophisticated evaluation, akin to an artist scrutinizing their masterpiece. The key elements of this process are fascinating. First, the judging is done in the same vein as instruction following. Think of a chef tasting their own cooking and determining if it meets the recipe's standards. Then there's the multi-criteria rating scale, a nuanced tool that evaluates the model's outputs on multiple dimensions, much like a wine connoisseur assessing a vintage on aroma, taste, and color. And as the training iterates, this evaluation ability gets sharper and more refined, like a musician's ear becoming more attuned to subtle notes and harmonies over time. This slide isn't just showing a process, it's revealing a journey of continual self-improvement and mastery. Now, let's illuminate the remarkable results in instruction following. Picture a graph that vividly showcases the win rates when pitted against the GPT-4 evaluation standard. This isn't just a set of numbers, it's a story of progression and triumph. The figure delineates head-to-head win rates, not only against a baseline, but also across different iterations, all evaluated by the keen eye of GPT-4. Imagine a series of races where each iteration is a runner, each striving to outpace the last. Iteration 1 starts strong, matching pace with the baseline, like a newcomer proving their mettle. But then Iteration 2 leaps ahead, significantly outperforming both the baseline and its predecessor, Iteration 1. It's a display of growth and improvement, like a runner finding their stride. The climax is Iteration 3, outshining all that came before it, boasting a 62.5% win rate over the baseline. This isn't just a win, it's a statement. It's like watching an underdog rise to become a champion, surpassing renowned contenders like Claude 2, Gemini Pro, and GPT-4 0613 on the Alpaca Eval leaderboard. This graph doesn't just show numbers, it narrates a tale of clear, undeniable gains from an iterative training approach where the model is honed and refined by self-generating training data with each round, akin to a blacksmith forging a sharper sword each time. Transitioning smoothly to the realm of reward modeling results, we witness a fascinating evolution in the model's evaluation capabilities. Imagine a graph that steadily ascends with each iteration, a visual metaphor for growth and improvement. With each cycle, metrics like pairwise accuracy don't just increase, they soar, painting a picture of a model that's not just learning, but flourishing. By Iteration 3, we reach a pinnacle of success, with the model achieving its best results across multiple metrics. It's like watching an athlete smash personal records in every event. This isn't just progress, it's a validation of the groundbreaking idea at the core of this research. The model's understanding of what makes a good response isn't just improving, it's being transformed through the innovative self-rewarding mechanism. It's a testament to the power of self-improvement and continuous learning, a beacon of what's possible when we rethink traditional approaches and allow models to become their best judges. In a grand summary of this groundbreaking work, we encapsulate the key contributions that mark a significant leap in the field of language models. First off, the concept of self-rewarding language models, a revolutionary idea where models are not just learners, but also their own judges, thanks to the LLM as a judge mechanism. It's akin to an artist who not only creates, but also critiques their work. Next up, the Joint Training Framework, a brilliant strategy that enables simultaneous improvements in instruction, following, and judging. Imagine a juggler who gets better at both tossing and catching with each throw. Then, there's the iterative pipeline, a self-sustaining cycle where models self-generate and learn from their own training data. It's like a chef who cooks a dish and then uses the experience to refine the recipe. The key outcomes of this venture are nothing short of impressive. By moving away from the limitations of fixed external reward models, this approach has unlocked new levels of capability enhancement. It's as if we've been given a new lens to view the potential of language models, revealing the possibility for models to surpass the boundaries of human seed data alone. This isn't just a study, it's a pioneering exploration into the realm of self-improving models, opening doors to exciting new research directions and possibilities. It's a glimpse into a future where models are not just tools, but collaborators in their own right, continually evolving and surpassing our expectations.